Hello everybody, welcome to this video. In this video we're going to be looking at exponential growth and decay, and I think that these notes are going to be pretty easy compared to some of the last things that we learned. The first function it wants us to use is y equals 2 to the power of x, and we're going to build the table for that. For the first part of the table, we're just going to fill in these x's where they go in the formula. So we're going to take them and we're going to put them up there as an exponent. 2 to the power of negative 3, 2 to the power of negative 2, 2 to the negative 1, 2 to the 0, and continue. Then we'll type into Desmos y equals 2 to the power of x. I would hope that you already know how to do a custom power in Desmos, but you can push a to the b, and then you can put an x up there. Looking at the graph, it makes this curve, which does have a horizontal asymptote from left to right, which we saw in irrational functions. But to finish this table, let's convert it to a table. The ones that are pre-filled are from negative 2 to positive 2, so let me just copy those down first. And I'm going to put the decimal form and the fraction form. And now let's get those last ones that we didn't get already, like negative 3 and positive 3. With these numbers, we can graph it. Negative 3 goes with 1/8. Negative 2 goes with 1/4. Then a half. Then 1, 2, 4, 8. So as you go to the right side of the graph, as you go to the right, you should see a large amount of growth. So as x increases, the y will also increase. And as you go to the left, these x's, the more negative that they get, it's just going to make the y a smaller fraction, but it'll never turn into a negative y. So we create an asymptote that'll get closer to 0, but not be equal to 0. And you should put an arrow on both sides of that graph. An exponential function is a function of x that could have a multiplier in the front, then a base value, and that base value gets raised to a power of x. I'm going to write this extra part anyway, but sometimes it isn't there. A lot of times there will be another type of scale factor that happens directly to that power. Some formulas will have a k next to the x, and some formulas won't. If you make it to calculus and higher maths, then you're going to be used to seeing a power of kx. So I'll leave that there just in case it shows up at some point. Or you can just use these easier versions down here. For exponential functions, it means you're either repeatedly multiplying by something and it's making you grow, or you're repeatedly multiplying by something and it's making you shrink. If you're growing every time you multiply, that means it's exponential growth. And if you're shrinking every time you multiply, that means exponential decay. The way you can tell if you're going to grow or shrink is whether the number that's being raised to a power is greater than 1. If the number being raised to a power is between 0 and 1, then that would be kind of like multiplying by a decimal, and multiplying by decimals would be a shrink or decay. putting the absolute value because it is possible for the b to be a negative number, and you would just look at the absolute value of that b, and if it's greater than 1, it's going to make you grow, and if it's between 0, the absolute value of that factor could make you shrink. A lot of times it'll be useful in a real world situation to, instead of just saying you're multiplying by a certain scale factor, to talk about that scale factor as a rate of increase. The rate of increase uses the number 1 as a baseline, and then however much you are above the number 1 would be your rate of growth. So b would be equal to 1 plus r, where r is your rate of growth. And later in the notes, I'll show you how you do a rate of decay. The rate is usually measured as a percent. For example, you could do a 25% increase, which would mean your b would be equal to 1 plus 25%. You would convert that percent back to decimal form by moving the decimal 2 spaces over to be 1 plus 0.25, which would give you a b of 1.25. Where it says initial value, you could put that as x1, y1, or instead of putting x1, you could just put 0, which would mean that it's also the y-intercept. You can find the a value by just looking at the y-intercept of whatever situation you're dealing with. Let's use this formula in an example. We have a population of 281 million people. That sure sounds like a starting value, which is a y-intercept. We're increasing by 1.24%. That's an r. That's not the b, that's the r. Okay, so the growth factor is the b. We need to solve for b, and b is just 1 plus the percent increase. 1 plus 1.24%, which is 1 plus, move the decimal 2 spaces, 0.0124, 1.0124. Now that we have the b, we can use that to write the formula. Y equals a b to the x, which would be y equals the starting value, 281 million, and the percent increase is, or 1.0124 to the power of x. For the last part of this example, they want us to use the year 2025. 2025 is either going to be an x or a y. If we go back to the original story, it says that we're starting at 2000. We got 281 million people to start with, and then the annual rate of increase is 1.24%. Annually means every year, so that means we're counting this by the years. In exponential growth, you really need to keep track of what the time periods are. And that's what this is saying up here in this formula, the number of time periods. Maybe in certain situations it'll count by weeks, some situations use months, some use semi-annually, and some use yearly. In this question, we're starting at 2000 and we're counting every year after 2000, which means 2025 is x equals 25. So we'll copy the formula from part B, and we'll plug in 25 at the top, and then we'll put that in a Desmos and see what our answer is. Here's the number I get. Since we're talking about a population of something, that means that these are people. So if this says if it ends in 0.564 people, you're going to round that down, since 0.56 of a person is not a whole person, and with people you only have whole amounts. So we'll copy that number, 382, 392. $822, and you're not going to round up. In these next questions, we're going to graph them, and then we're going to convert it back to get the y-intercept and the growth factor and domain and range. So we'll type it into the calculator. To copy the graph from Desmos to my paper, I'll need to turn it into a table. That way we can see the specific numbers, and we can copy these good numbers, 1 with 3, 2 with 4.5, 0, 2, -1, 1.3, and -2 goes with a little bit less than 1. You can look at Desmos to make sure that the horizontal asymptote is getting closer to 0, but not passing 0. And then you can connect this graph back. The initial value is the y-intercept, and the y-intercept was 0, 2. The growth factor, let's look back at our definitions. The growth factor is whatever b is. So b is the number that's being raised to a power. And in this question, we have 1.5 being raised to the power. So the growth factor is 1.5. Domain, if you look at the graph, it's going to go forever to the left, forever to the right. So it goes from -infinity to +infinity. For the range, going down, it doesn't include 0, but it does get to be every y value greater than 0. You can try the next one on your own, and then I'll post it in about 10 seconds.